Hi everybody, we are Group 5. We'll be presenting Lab 2. The group members are the following. Victoria Ackerman, Alberto Contreras, Esteban Tunidor. We all had the same level of contribution. These are the topics we'll be presenting. We'll be presenting them pretty quick because of the time that we have. But we'll focus on the Boolean equations. We know how to get this equation by getting the ones that have one input and putting it here. And then we just add them together. Here it's really hard to make a logarithm out of this. We have to reduce it, and this time it was hard to do with Boolean algebra. That's why we learned we're going to learn a little bit about K-maps. So here, this is if we were to go ahead and just do it in logarithm. Really hard, really complicated. This is how it would look like if we simplified it. Pretty easy. Here's the equation. That's better. That's how they look side by side. The hardest part is reducing the equation, and we'll show you how to do it through K-map. This is how a K-map looks like. This is the truth table. We use the truth table to fill in this part of the K-map. These are mean terms. They are known as mean terms. We start with M0. And the way to fill out the K-map, you put M0 here, M1, you skip this one, M2, M3, you do the same thing here. Then the tricky thing is you skip this line and then you go M8, M9, skip this one, M10, and then fill out this the same way we have been doing. That's really an easy way to do it. I just focus on the ones. Okay, I have 3 ones here, so 1, 2, skip 1, 3, and then just the rest of them zeros. That's the way I do it. K-map equations. Now we go ahead and simplify. Now that we filled it out with the truth table, we can group in powers of 2. That means groups of 2, 4, 8, or 16. So if we group power of 8 here, we're able to reduce it to one variable. If we have a group of 4, we're able to reduce it to 2 variable. Okay. This is how we group them. As you can see, the only thing that stays the same is the C naught in the orange circle. In the purple, you compare it here and here, and you compare it here and here. So the one that stays the same is B naught, and here D naught, as you can see. We implemented the circuit. This is how it looks like. Using the integrated circuits, we have a lot of knots here, a lot of OR gates here, and then AND gates here. So we just do the same thing. We just have to know where's the ground in all of them. Okay, and that's how we implement them. This is just basically connecting all of them together. Using NAND gates, we actually, when we did the NAND gates, we realized that the equation even got smaller because you can eliminate NAND gates when you connect them together. They cancel each other. So we were able to reduce it to this. So this is how it looks like an integrated circuit. If you open an integrated circuit or the logic that goes inside of it, this is how it looks like. So there's four NAND gates. So we were able to implement it. As you can see in the previous one, that we needed 4 NAND gates. That's specifically the amount that we have in 17400. So we were able to implement it easier. Our conclusions was that K-maps is a convenient and easier, faster way to simplify the Boolean equations. Simplified equations reduce the number of gates needed. Small number of gates will reduce the cost of the system. We thank you for watching. Hope this will help you in future labs, and it makes you more aware of how the integrated circuits work and NAND gates. Thank you for watching. Don't forget to evaluate our performance.